And so first of all, I'd like to thank the organizers. So today I'll be discussing some aspects of black hole information paradox with the talks of Siddharth and Chandramouli yesterday in mind. So Siddharth told us something very fascinating yesterday. He said that in a theory of quantum gravity, all the information is stored at the boundary. So quantum gravity is non-local. So in fact, if we consider this room to be the universe, then all the information about this room is stored, for example, in these walls, the floor, and the roof itself. So if I were to push this table, then this perturbation can be measured from the boundary instantaneously. We don't need to wait for some signal to go from this table to the walls. This can be done instantaneously, and in fact, Chandramouli talked about how we can do this in practice by just measuring some small two-point correlation functions. So now what we'll discuss today is what does this imply for the information paradox. So before doing that, let's just briefly review what the paradox is. So suppose we start with a black hole, and the horizon of the black hole is smooth, but this, and initially the system is in pure state, but eventually this black hole will start radiating via the Hawking process, which essentially happens from the horizon. So these radiation which go out doesn't have a lot of information. It only knows about, for example, the mass, the angular momentum, or the charge of the black hole. And eventually the full black hole just evaporates, and we are just left with a mixed final state. So it seems that this process is non-unitary, and which is against quantum mechanics. So this is what we generally call the naive information paradox, and it's naive because it's not really a paradox. Just keep this in mind, this is not a paradox because suppose we take a microcanonical ensemble which has entropy S, then any pure state which we pick at random will mimic a mixed state with exponential accuracy. By this, what I mean is that if I take any observable and measure it in this pure state, then it will be same as in the mixed state with some exponentially suppressed corrections. So in fact, the calculation of Hawking is not precise enough to give us a paradox. So what we expect is that the radiation which comes out will indeed carry all the information about the state of black hole eventually. And in the end, we'll be left with a pure state. So before moving on to the real information paradox, I just want to talk about a few things from quantum information. So the first concept I want you to remember is the notion of von Neumann entropy. So suppose I have a system A, which is in some mixed state, then von Neumann entropy, what it does for us is it tells us whether the system is in a pure state or a mixed state. So if the von Neumann entropy is non-zero, then the system is in a mixed state, otherwise it's in a pure state. The second thing which I want you to keep in mind is this notion of purification. So suppose I take this system A, and then I ask the question, can I club it with another system B such that the system A and B combined is in a pure state? And in fact, we can do that if this system B is entangled with the system A. And for example, if we choose the state to be this particular entangled state, then we can see that if we just trace over the degrees of freedom in the system B, then we'll just get back this state. So keep this in mind. And the third thing which I want you to keep in mind is the notion of monogamy of entanglement, which is the notion that if we take three separate systems, A, B, and C, then any system, for example, B, cannot be simultaneously entangled with A as well as C. So this, for example, is used in quantum communication, secure quantum communication. So just keep these three things in mind when we build up the paradox. So before doing that, let's study this, do a thought experiment. We take a lump of coal and we burn it. So initially, there's no radiation. And to be precise, I'll define everything apart from the coal as the radiation. So initially, there's no radiation. So it's in a pure state. So the von Neumann entropy of radiation is just 0. But as the coal begins to burn, the radiation is emitted out. And this radiation is, in fact, entangled with the degrees of freedom in the coal. So this von Neumann entropy will keep on going up. But eventually, when all the coal is burned, we expect the von Neumann entropy of the leftover radiation to be 0 just from unitarity. So there should be a time when this graph just turns around. And in fact, it turns around when almost half of the coal is burned. Because what happens is that the remaining remaining amount of coal which is left is now entangled with the radiation now. So if the next quanta of radiation is already entangled with the radiation which we have, so it can purify the radiation. So that is why this 1 Neumann entropy goes down. So this entanglement was necessary. So now we expect some similar thing to take place in the case of black hole evaporation. Initially, the radiation, the entropy of the radiation should be 0. It should go up and finally come down just from unitarity. So what is the paradox? The paradox is the following. So suppose I take a time, I take a particular time shot of this system and divide my full space in 3 regions, A, B, and C. A is the black hole, B is the radiation which is going to come out of the black hole, and C is everything else. So in the next instant, and this time corresponds to this particular line where we have crossed this this peak. So what we expect is the following: that what we expect is that B should purify C just from unitarity, but it can purify C only if B is entangled with C. But note that black hole. The horizon of the black hole is smooth, and it's a good dictum to remember that in quantum field theory, whenever we talk about something being smooth, then there would be entanglement. So smoothness of horizon would imply that A and B should be entangled. So this leads us to a paradox, because now B is entangled both with A and as well as C. Which violates monogamy of entanglement. And in fact, small corrections is not going to help us. It's an order 1 paradox. And this is really the not so naive version of the paradox. But and note that this is not a paradox for the coal, because there is no constraint of smoothness of horizon in the case of coal. So A and B need not be entangled. But again, this is not a paradox. And this is not a paradox because, as I talked earlier, that quantum gravity is not local. So all the information is just contained in the boundary, and the boundary is contained in this region C. So all the information is already there in C. So in fact, everything, every information about the state A is contained in this state C, as well as same goes for B. So we cannot think of these 3 regions to be separate Hilbert space, if you want. So these are not different systems. These are all contained in C. So yeah. So in fact, because C knows about the full state, the 1 Neumann entropy of C we should expect to be 0 all the time. So we shouldn't expect this S radiation to go up and then come down. It in fact should always be 0. Now you can ask me whether this is important for the burning hole. But before that, let me point out that this is always important for the black hole. And the reason is that so suppose we take a microcanonical ensemble, and what we really want to do is that given some state, we want to know whether this state is in a pure is pure or mixed. And this is not something which we ever do in experiments. It's a very complicated question, and to do that, we would need to measure correlators which scale with the entropy. And in fact, the black hole entropy scales inversely with the Planck length. So, and it is so large that there is no way we can do these measurements without changing the geometry itself. So essentially, the perturbation theory breaks down, and non-locality cannot be ignored. But in the case of burning coal, this may not always be the case, because we are really looking at a very different physical process. The entropy of the coal comes from some chemical reaction or as such. So it has nothing to do with the Planck scale. So it may be possible that we can ignore this effect, but it's extremely unlikely, because the corrections which we want to measure are of the order of e to the power minus s, and entropy would almost scale as some 10 to the power 23. So to determine whether a state is pure or not, we might just run into quantum gravity corrections. So I'd like to just end by saying that that information paradox revealed something very deep about nature of quantum gravity. It was related to this notion of non-locality. If you take nothing out from this talk, just remember that quantum gravity is non-local. And in fact, there's another version of information paradox, if you want, information paradox 2.0, which is not resolved by loss of locality. It has to do with whether we can define operators behind the horizon or not, which I'm not going to talk about. And the resolution to that paradox also is, it tells us something very fundamental about quantum gravity. Again, you can ask me for more information later, but with this, I'd like to end. Thank you.
Any questions?
First slide. Yeah, this. So what's the question? Nothing. Yeah.
So can you go back to this coal example where you say that the radiation of entropy increases and it decreases?
Yes.
So what is this entropy? How is this entropy defined? It's
So this is the von Neumann entropy. So this is just trace rho log rho of the everything apart from apart from the coal. So in fact, this we can do for so suppose we take some Hilbert space, some system which has a very large dimension. Some, let's say, m into n is the dimension of the Hilbert space, and we divide the Hilbert space into two parts, one which has a dimension m and the other which has dimension n. Then what we can argue is that the von Neumann entropy of the system, let's say if we trace out one of the part, will just be related to the dimension of the smaller Hilbert space. And this we can do, I mean, this is a very general argument which we can make.
So if you define von Neumann entropy of the one half of the system,
yes,
then suppose you have unitary dynamics for your microscopic degrees of freedom.
Yes.
But often it looks like it is believed that if you define the von Neumann entropy of one half of the system, then the evolution of that entropy will not be unitary.
Yeah.
Do you expect
so what I'm trying to
only if you define the von Neumann entropy of the full system,
yes,
then it will never change also, I guess.
yes, and that is what happens in gravity, because the degree of freedom which I was calling as radiation is in fact all the degrees of freedom. So that is what happens in gravity. So von Neumann entropy never changes. But here what is happening is that initially we started with coal, finally we are just left with radiation. So if initially the state was pure, the full state was pure, the full state of the full final state should also be pure, which is just the radiation in this case.
Yeah, but when you associate that the initial state describes coal and the final state describes radiation,
yes,
you have a macroscopic description, and if you want to do some entropy calculation from this macroscopic description, you'll have non-entity evolution of the entropy.
So yeah, of course. So for example, if I just want to look at this coal and study the von Neumann entropy of this coal, then of course the evolution would be non-unitary. I agree. The von Neumann entropy will change. But if you look at the whole system, the only thing what I want to do is that if you look at the whole system, the evolution should be unitary. And that would basically amount to the initial state and the final state being pure. That's all. Yeah. Yes. Yeah, so I'm not really looking at de Sitter space. In fact, we can do this for flat space and anti-de Sitter space, but we can't do this in de Sitter space. Yeah, I'm making that assumption. In flat space, you can do that because you can just make a conformal boundary, so you can just compactify the spacetime and yeah, there's this notion of Penrose diagram that you can define a boundary and then do this more precisely.
Now let's thank the speaker.
Thank you.